So I will start again with some Hebrew. אוקיי, שלום לכולם. אני מניח, מקווה שאנשים נוספים ונשים יגיעו לשמוע את הסדנה הזו. אני מתחיל פשוט בעברית בדיוק שתי מילים, רק להגיד שאנחנו נעבור לאנגלית, ומי שיריץ את הסדנה הזו זה ג'ון סטרמן, שעוד מעט אני גם אציג אותו. אז זהו, אז זה הנוהל שלנו ואנחנו נתחיל. So I'll switch to English, and I would like to, and I'm very happy to introduce Professor John Sterman, who will be leading this workshop on his En-ROAD simulation and model and application. Professor Sterman is a leading climate scientist and the J.W. Forrester Professor of Management at the MIT Sloan School of Management. He holds a PhD in system dynamics from MIT and has made significant contributions to understanding complex systems, particularly in climate change and environmental policy. He has published extensively, more than 300 book chapters and articles in leading scientific journals, and has almost 58,000 citations, which is really, really impressive. He is a recipient of many awards, and we could actually stand here forever just to list the awards, but I would like to mention the Systems Dynamics Society's Lifetime Achievement Award. Professor Sterman is currently the director of the MIT System Dynamics Group and a prominent figure in the fields of system dynamics and sustainability. With respect to the latter, I would like to also mention that he's the co-founder and faculty director of the MIT Sloan Sustainability Initiative. His research and teaching have had a profound impact on shaping global strategies for sustainable development and climate action. The reason for that is his groundbreaking work, including development of different models, and especially the one that we are going to talk about today is the En-ROAD, which is widely used to explore climate solutions. So we are gathered here today to hear Professor Sterman present the En-ROAD model and its capabilities. He will describe the model and run some interactive simulations with us, the audience. So be ready to be interactive in the next hour and a half. So thank you very much, John, for your willingness to share your work with us. And it is in your hands now. So go ahead. Thank you.
Great. And thank you so much, Yaron. It's a pleasure to be here. And I'm only sorry that I can't be there in person due to schedule constraints with my teaching commitments here. So the first thing, I appreciate the very generous introduction, but what I want to stress is this will be interactive. And so I am going to be asking you all to tell me how you think we can solve the climate crisis using our interactive En-ROAD simulation. I also urge you to ask questions and challenge me and disagree at any point. This is not going to be a presentation with Q&A at the end. Unfortunately, I can't see all of you, but you know, I am a professor in the School of Management, and that means we call on people. So I may at some point ask Yaron to just pick somebody at random and call on them. So let me get started with a very brief introduction and starting with what is the problem that we're trying to solve in our work? Why have we developed this interactive simulation? And I think you all know the reason. There's no longer any doubt that the climate is warming. The overwhelming cause of that is us, human activity, particularly burning fossil fuels, land degradation, other greenhouse gases. And climate change poses a grave risk to our prosperity, our health, our national security, and even our lives. And that's true everywhere around the world. This is now no longer in doubt. The problem is there's no agreement on what to do about it, and action lags far, far behind what's needed to create a safer, more sustainable, healthier world. So, for example, you're all familiar, I'm sure, with the emissions gap, the gap between the pathway we're on for global greenhouse gas emissions and the pathway that's needed to have a reasonable chance of limiting warming to, quoting here, well below 2 degrees C above pre-industrial levels and striving for 1.5. There's no agreement on what we should do. So just for example, here you see some of the commonly presented solutions, and often presented as, if we just do this one thing that somebody favors, problem solved. So is it renewables, wind, solar, hydro, geothermal? Is it nuclear? Is it fusion? I won't read the whole list. You can see it, but there's great disagreement. These proposed solutions are controversial and contested. Maybe some people say, maybe if we just plant 1 trillion trees, problem solved. Or if everybody eats less meat. Or others say, nope, we've got to have a price on carbon. Or nope, we've got to have carbon dioxide removal technologies and CCS. And fundamentally, there's a huge disagreement about whether the way forward can be met just with technological breakthroughs, or whether we need government policy and regulation, or whether we just need market solutions. There's no agreement here. So the motivation for our work is we've created an interactive tool that allows people to learn for themselves. So why do that? Why not just do the best modeling, publish it in the academic journals, and then brief policymakers around the world? And the reason is, well, let me put it this way. Research shows that showing people research doesn't work. And I know you've all been in endless, boring presentations where some expert shows too many PowerPoint slides, and as a result, nothing happens. And this is especially true when we're trying to present the results of our scientific research to policymakers and other leaders, people we need in order for policy and action to take place that can get us on the pathway we need. So just a little bit of background, we're going to get right into it. So at MIT, we've been working in my group, the Sustainability Initiative that I founded in 2006, and other activities. We've been working hard to address that problem. The problem is partly scientific. Of course, we need more research into how does the climate work, how does it affect other critical ecological and environmental systems, human welfare, social justice and equity, and many more. But that's clearly not enough. So our new president at MIT, Sally Kornbluth, initiated last year what we're calling the MIT Climate Project, which is an all of MIT effort to pivot the Institute to make a real difference on climate policy and action in the world. And that's more than just research. The foundations for this were laid with our work and that of others at MIT, including our Sustainability Initiative, founded in 2006, what we call the Climate Pathways Project, which is how we bring the simulator you're going to see today to government and other leaders around the world, and a brand new policy center that we're just standing up right now. So the missions of these activities are listed here, but I'm going to gloss this because you can go to our websites, and I'll provide the slides for your own to distribute to everybody after today's session. I also want to say, though, that I'm very proud to be a member of the External Advisory Board for the Goldman Sonnenfeld School of Sustainability and Climate Change at BGU, and working with Yaron and others, Danny Chamowitz, et cetera, to help catalyze this kind of activity here or there in Israel. So let me get right into it, and pretty soon we're going to put you all to work. So what is this simulator, and what is it really for? Well, as I said, research shows that showing people research just doesn't work. The way people learn best is from experience and experiment. But in the domain of climate and many of the other most critical systems that we are threatened by and that we threaten, experiments are impossible, and experience will come too late to make a difference. And this is a common situation. If you want to learn how to fly a fighter jet, you're going to learn not just in ground school, but in a simulator. you want to learn to be an effective surgeon in an operating room, you're going to train in an OR simulator. And it's the same story here, and I know you're all familiar with this concept. So the En-ROADS Climate Policy Simulator, which we've developed in partnership with Climate Interactive, which is a nonprofit, nonpartisan group founded by one of my former students. It's grounded in the best available peer-reviewed science and evidence. It's fully documented, as I will show you, and it's free. Anybody can go online and use it. And what users can do, well, you can read this, but that's not important. Let's actually go there and do it. So this is what it looks like.
John, just a second. John?
Yeah, go ahead.
Before we go into the mechanics, can you say a few words and tell us who is actually involved and what groups or world leaders are aware of, familiar with, and really use En-ROADS?
Great. So great question. Let me get out of PowerPoint and let's take a look at how it's being used around the world. So here's pretty up to date. I think it's a little out of date now, showing all the workshops that we're aware of. We know this is an undercount, where what you're about to do today or our other interactive experiences have been presented to audiences from senior policymakers to community groups in 169 countries. The number is now 380,000. And more than 15,000 of those people are leaders in government, business, and civil society. More than 1.5 million now have actually used it all over the world. So this is some of the reach. And just to give you an example, I've personally briefed over the last 3-4 years, actually starting in 2019, so 5 years, 36 members of the US Senate, more than 150 members of the House of Representatives, and a wide number of governors of states, of mayors, of city council members, many, many other folks all over the world, and many of their counterparts in other countries, Japan, China, India, the UK, European countries, the EU, etc. So, and I'm not the only one. Many, the way we get to 15,000 is with a team of folks who have been able to build their skills and use the simulation effectively in their areas. So, Yaron, anything else before I go on?
No, thank you very much.
So this is the simulator. This is not a slide. This is the simulator running live. Today, I'm going to try to show you the most recent development version. There's some features here I wanted to try out with all of you. If it develops a bug, which is always possible in pre-release version, we'll go to the public version, which is here. But let me explain what's going on. So first of all, it is available in 20 languages, including Hebrew, including Arabic, Chinese, Japanese, and many, many others here. And this actually makes a big difference. In January, I was in Japan for a week. I did 18 interactive workshops with senior ministers in important ministries, advisors to the prime minister, business leaders. I did them all using the Japanese version, even though I don't speak Japanese. This really, really makes a big difference. So feel free to use it yourselves. And if you find any errors in our translations, you just let us know. The interface has been very carefully designed to be easy for non-experts to use. So we've used state-of-the-art concepts in user interface theory to make it really simple. So you'll notice that the high-level interface, you have these linguistic labels here. So down here, you've got all of these policy levers. I'm not going to pull them now, but they say things like status quo, or if I take the population lever and I pull it, it says high growth or highest growth, et cetera. It doesn't give us numbers. Now, if you want the numbers, they're there under the hood. So we're using the UN's most recent population projection, 10.2 billion people expected by the year 2100. And you can see that by region here the United States and the EU way down here, other developed nations down here. China has already peaked. People believe India to peak in the next few decades. And then all the rest of the population of the world in the developing economies, Middle East, North Africa, Africa, Southeast Asia, other than India, Central and South America, et cetera, they are here. Now, if you, there's uncertainty here, as there are with many of the aspects here. So we've designed the model. So if you want to, if you disagree with this, or if you want to try other ideas of what population might be, you just grab this slider and move it. And as you move it, the simulation instantly runs and shows you the results for the economy, the energy system, and the climate. And that's one of the most critical features of this tool. It runs instantly. And if that weren't true, we would never be effective with the policymakers. I was at the US Congress last week presenting for I don't know how many times now to a set of Congress people. And, you know, if I had to say, well, let's try your idea, now let's go get a cup of coffee while the model runs, it would never work. So this is how it works. And I'm going to stick with the baseline assumption for population today. And now let me explain a little bit what's under the hood. And I want you to challenge us on this, right? All models are imperfect, as the saying goes from George Box. All models are wrong, but some are useful. And so in addition to my asking you all to tell me your ideas today about how we can create a pathway to a climate future with warming well below 2 degrees, I want you to challenge the model. Tell me where you think it's inadequate or needs improvement, because we're constantly improving it. About once a month, we'll update the model, either new features, interface, underlying model as conditions change. So this is a global model. We do have a regional model, but we're not going to work with that today. So one of the immediate ways in which this model is imperfect is it's a global model of the economy, the energy system, and the climate, and how they all interact. So what's going on here? This graph on the left shows total global primary energy use by source. Coal is brown at the bottom, oil is red, fossil gas, so-called natural gas, is blue. In the model, wind, solar, hydro, geothermal, and other renewables are all modeled separately because they have different costs and supply curves and rates of technological progress, but they're all producing essentially zero carbon power, and so they're added together in the green wedge of renewables. Likewise, there's 3 ways to make bioenergy from crops and crop residues, from wastes, and from wood, and then nuclear power is on top. We pay careful attention to how well the model replicates historical behavior. So here, for example, you see the marginal cost of solar photovoltaics, global average, the data thin lines, the model is the thick line. And it's very important for you all to know the model simulation here is not the result of running a regression on these data. Instead, the model's pathway for the cost of solar PV and everything else is the result of the endogenous interaction of all of the elements of the model: costs, subsidies if they exist, supply curve issues, people's behavior, how they choose among the different energy sources at the consumption level, and investors and utilities deciding how much to invest in each way to produce power or energy. Not a regression, but the endogenous interaction of all the elements in this very complex system. And from 1990 to the most recent available data, the model does a very good job here. Not perfect. And then here's global average surface temperature, also from 1990. And again, we don't attempt to capture the year-to-year fluctuations, El Nino, La Nina, et cetera. But the model tracks the evolution of global average surface temperatures extremely closely. And you'll notice we do include the historical exogenous perturbations here, the explosion of Mount Pinatubo, and then warming accelerated after that sulfate fell out of the atmosphere and put us back on the trend that we were on. So there are literally dozens more comparisons of the model against historical behavior that you can access online, and I'm not going to do that right now, where you can drill down and say, you know, how does the model do on replicating solar or nuclear or energy prices or coal production or whatever you want. So what does our base case do? Well, we have population driving this growth in energy demand. We also have economic growth. And, you know, again, you can look at GDP per capita by region, and you can change all of these assumptions as well. I'm not going to do that right now for time. There's also technological progress. So, for example, if we look here, the amount of energy needed to produce a real dollar of economic output has been falling about 1.1% per year. And we're assuming it's going to continue to fall through the end of the century. Now, why? Well, technological progress, also the gradual shift around the world as economic development occurs from a more industrial, heavy industry economy to a more service and information-based economy that uses less energy. But there is something very important. We've endeavored to include in the simulation all the climate policies that are in effect today around the world. So, for example, the EU's, the European trading system, the EU carbon pricing system, or in the United States, the Inflation Reduction Act. However, we do not include pledges and promises in our base case. When a country or a company went to Dubai last year for the COP, or going to Baku in a couple of months for COP29, and they say, we pledge to be net zero by 2050 or whatever, that's just hot air until they do something. So pledges and promises are not in our base case. And so what you'll notice here is that in the base case, there's significant growth in energy use around the world due to economic development and population growth. It's slower than economic growth because of the technological progress, but there's still growth there. Most of that growth is met by rapid expansion of renewables. However, that leaves a global economy heavily dependent on fossil fuels, coal, oil, and gas. And that leads to this pattern on the right of greenhouse gas emissions measured in CO2 equivalent gigatons per year. So the gray band here is the largest contributor to global warming. And that, of course, is the CO2 that's emitted into the atmosphere from burning the coal, oil, and gas, the fossil fuels, by far the largest contributor to warming. The second largest is the light blue, that's methane. And as I think you all know, most of that is coming from leakage from the energy system and industry and from agriculture. Then the third largest source is the green band at the bottom. That's CO2 emissions from deforestation and land degradation, LULUCF. And then we have nitrous oxide in purple and the fluorinated gases here. Now the model keeps track of about a dozen individual species of fluorinated gases, sulfur hexafluoride, different species of CFCs, HFCs, and so forth, HCFCs, because they have different contributors to radiative forcing, different atmospheric lifetimes, and different emissions budgets. But here you're seeing the aggregate of the fluorinated gases. So what that means is global emissions, which are at an all-time record today, grow somewhat more, roughly flatten out, but that steady flux of emissions into the atmosphere leads to steady temperature increase. So this is global average surface temperature. And as I showed you, it matches the historical data. And then the projection here is that we breach the 1.5 degree Paris goal by the end of this decade, 5 years from now, if not a little sooner. And then we breach the 2 degree threshold by around mid-century, and it just keeps going up. 3.3 by 2100, and it would continue after that. So one of the things that we've tried to do in the model is capture some of the impacts of this. So you can look at a wide range of impacts. I'm going to focus on just a couple for right now. So one is air pollution from fossil fuels and the energy system. So this is PM 2.5 emissions, global emissions of PM 2.5. And as you all know, this is one of the most harmful air pollutants. World Health Organization tells us this is prematurely killing about 7 to 8 million people every year, harms labor productivity, hurts the performance of kids cognitively and their performance in school. Just to put that 7 to 8 million premature deaths every year in perspective, here we are about 4.5 years, almost 5 years since the pandemic. The total official death toll from COVID is about 7.5, 8 million people. So this is a COVID worth of death every year from that air pollution. What else? Well, crop yields. Crop yields are expected to fall as a result of warming and climate change. You all know why: extreme weather, drought, floods, increasing ranges of pests and diseases, and so forth. And these are the big four grains that, of course, feed most people on the planet. Double-digit declines relative to what crop yield would otherwise be are projected for corn and wheat, and almost 10% for rice and soy. And this is in a world where we're expecting 2.1 billion more people that need to be fed by 2100. Other impacts that we're trying to capture here, I'm not going to show them all: wildfire danger, deaths from extreme heat. This is worth taking a look at, I guess, in different regions of the world. As you would expect, deaths from extreme heat are projected to be highest in places like Southeast Asia, Southern Europe, the Middle East region, the Mediterranean basin, Africa, South America, because that's where it's already the warmest now, and that's where wet bulb temperatures are highest now, and people in the developing countries are least able to find air conditioning, and many more of them than in developed economies are engaged in agriculture and construction, outdoor work. So these are serious problems, but let me show a couple others really quickly. So one of the things we've done is we've...
John?
Yes, sir. Please go ahead.
Someone wants to ask a question, if you don't mind.
Great. Go ahead.
Thank you so much for the presentation.
Yaron, I'm not able to hear.
It's okay. She's coming here.
Great.
Thanks so much for the presentation. Just before you go on, if you could just clarify, because I see some of the levers here are not in the middle, right? So is this the baseline that we're looking at, or did you already kind of move some of these levers around?
Great question.
Clarifying questions.
Yeah, it's a great question. So, for example, so the baseline represents the status quo, which includes all the policy actions like the Inflation Reduction Act in the US that are in place today. So if you contrast, say, the coal lever against the renewable lever, the presumption is that few people are going to want to incentivize more coal production. So we've got more room on the left. If you were to drag, and I'm not going to do it right now because it's up to you to tell me what you all want to try. But if you were to drag this to the left, the farther to the left that it goes, the more aggressive are the policies and actions that would disincentivize or reduce coal. On the other hand, presumably most people don't want to disincentivize renewables. You have a little room here on the left to do that in case you wanted to test a policy that perhaps would correspond to what would happen if political leaders were elected who were hostile to the idea of climate change. But most of the room is on the right. And as you pull that lever to the right, you would be increasing the incentives for faster adoption of renewables. So that's the reason, right? And likewise here, few people are going to tell us we should have more deforestation. Most people want deforestation to fall. Does that help?
Yeah, thank you.
Great. So what I was trying to do, and remember, this is a development version. So we have worked with folks at MIT who helped us develop a regionalized, geographically very granular assessment of temperature. So in the baseline, we have 3.3 C of warming above pre-industrial by 2100. And here, what we can do is we can look at anywhere in the world, and ask what, in that scenario, at 3.3 global average, what is the expected temperature anywhere in the world? And, so for example, here you see 11 degrees C in the Arctic. That's, of course, the result of Arctic amplification. But let's come and look at Israel. So let me come back down here. 3.3 average. And, so you folks are down here now, right? So 3.7, it's higher. And you all know why, right? The oceans don't warm as fast as the land. And it's very valuable to look at your neighbors and ask what destabilizing consequences there would be with this kind of warming in those regions. So, so that's a feature we have now. We have some other useful features. So for example, let's talk about sea level rise. So in our baseline, using IPCC sea level estimates, you're looking at 70 centimeters of sea level rise by 2100. Most people, so this is out of date because it's AR6, which is many years out of date now. Most people in oceanography and looking at the melting possibility for Greenland and Antarctica believe this is too optimistic. So one of the features in the model is that you can change a huge range of assumptions about how does the climate work, about fire, about the carbon and methane cycles. And I'm going to illustrate this by changing the sea level story. And, just for illustration, this might be more consistent with current understanding of the contribution to sea level rise from melting of Antarctica, West Antarctica in particular, and Greenland. Now you're looking at about 1 meter of sea level rise by 2100. Well, what does that mean? One of the other features that we have here is we can look at sea level rise anywhere in the world. And it's not going to be a huge issue directly for Israel, but here's the Nile Delta. And that is a very serious geopolitical risk and national security risk for Israel. But let me show you that it's not just in the Middle East that matters here. Right now, today, we're expecting landfall of a major hurricane that's sweeping across Mexico right now. This is sea level rise impact in the Gulf Coast of the United States by 2100, and it's devastating. Now, the model's free. I'd encourage you to try this out yourself later and look at any part of the world you want to look at. Here's Shanghai in 2100, and this is devastating. And of course, this is optimistic because it doesn't show what happens when there are storms like typhoons that can hit and have hit Shanghai or New Orleans or the Philippines. And so let's put a 3.5 meter storm surge on top of this 1 meter of sea level rise, and you've got a devastating catastrophe. So there's other impacts that we're modeling, but I don't want to use the time to go through them, other than I want to show you that all of these impacts and all the other impacts of climate change that we're not yet able in a grounded, scientifically accurate way to model, they are expected to have serious economic consequences. So here you're seeing GDP per capita, real economic output per capita. The dashed line is what would happen to prosperity around the world if climate change had no further impact on the economy, which we know is false. And the solid line is the actual pathway for economic growth. And there's a significant and growing loss due to the harms from climate change that you're seeing here and all the others. So, you know, sometimes people tell me, oh, well, you know, sure, climate change is going to slow down economic growth, but it's still growing. But what I want you to do is look at this right there. That little drop, that is the economic harm from COVID globally. We all lived through it. We all, perhaps many of us, including myself, we lost friends and family, and we all experienced the economic hardship. I got to tell you, what's coming at us from climate change in terms of the loss of economic growth here makes COVID look like an insignificant blip. So your challenge, and here's where we're going to go. Your challenge is now to suggest to me, to tell me which of the many policy options you've got down here you would like to try that you think have high leverage to bend this emissions curve down and limit the warming to well below 2 degrees. So over here on the left, you could disincentivize, discourage, regulate, phase down, phase out coal or oil or gas. You could disincentivize or promote bioenergy. Presumably you'd want, as we mentioned, to promote renewables or nuclear. New zero carbon electricity represents something a little different. It represents the possibility of a radical technological breakthrough like fusion power that would produce 100% carbon-free electricity. So I want to point out, you can try this. You're welcome to try it. We added it to the model sort of at the request of Bill Gates, who was always saying we just need fusion and we just need technological breakthrough. But notice there's a difference. If you tell me you want to encourage renewables, we know exactly how to do that, and it's already happening today. Tax credits, production tax credits, investment tax credits, low interest financing, loan guarantees, outright grants, other government policies to promote the adoption of wind and solar and so forth. We know how to do that. New zero carbon, though, like a breakthrough that would lead to practical fusion power, nobody can guarantee that that breakthrough will ever happen, and it certainly cannot be scheduled. So if you ask me to try it, which I'm happy to do, just remember, you can't guarantee it's ever going to happen. The other option you've got down here is you could put a price on carbon above the current prices we have. In the middle, you could accelerate improvements in energy efficiency, and you can electrify transport, buildings, and the built environment, industrial processes. Over here, carbon dioxide removal, nature-based CDR like afforestation or agricultural policies, technological CDR like direct air capture or enhanced mineralization. You can reduce emissions from agriculture. You could reduce deforestation faster than the base case assumes, and you can reduce emissions of the fluorinated gases, the nitrous oxide and methane from wastes and leakage from the energy system. So, I'll say one other thing before we turn it loose. Every one of these things, you've got a set of advanced options that lets you drill down. I'd say because of the limited time we have, let's stick to the high level, but I'm happy to drill down. But the other thing is there's documentation here. So if you click on any lever, it tells you what that lever means. And if you click here, it tells you examples of what this lever would mean, gives you some idea of what those technologies are. And also we consider the equity issues. What are the potential co-benefits in biodiversity, in the hydrological cycle, in jobs, and so forth, and social justice and equity considerations. So that's there for every policy option you've got. So we're in trouble. This is carrying us to catastrophe. What do you want to try? So Yaron,
yeah,
go ahead.
Just very, very, very briefly, it looks like a computer game, and, you know, some scientists or other people may say, you know, this is just a relationship between different entities and so on. Can you just show briefly, if people want to see the equations, understand what is the science behind it?
Great.
Can you where we can find it, the scientists, the people that want to understand the mechanism?
Terrific. So it's a great question. So first of all, the underlying model is a large system of nonlinear differential equations. So it's a physics-based model. It's a mechanistic model. It's not a machine learning set of correlations or a big regression model. It's intended to be a causal model of how the energy system, the economy, and the climate work. And you can go and see the full documentation. So if we go here, there's all of these support resources for you, but the documentation is here. And if we open it up, you can get a high-level sense of how does the model work. And then you can drill down and look at the overall model structure, how it's simulated. And well, let me just pick one at random here. Here's the climate sector. So there's an explanation and the equations in standard notation. I'm not going to spend time on this, but how does radiative forcing affect the heat flux and the heat balance of the planet? How does transfer of heat? Here you can see a model diagram, heat in the atmosphere and the surface layer of the ocean. Radiative forcing increases that stock of heat. There's then radiation back to the cold of space. There's transfer of heat and carbon dioxide from the surface layer of the ocean to the deep layer. We have, I think, 4 layers of the ocean here. And then you can look at every equation interactively. So here's temperature change since 1850. And here's the equation. And then you can just keep going through. Here's the change in the stock of heat in the atmosphere and the upper ocean is the integral, the accumulation of total radiative forcing, less the cooling of energy being radiated back to space, less heat transferred to the deep ocean by layer. So you can then trace this back to see every equation in the model. You can see what the parameters are and what are the sources for each of these different things. So invite you all to do that at any point that you like. And like I said, we are very interested in critiques and suggestions for how the model can be improved.
This is wonderful. Okay? I'm convinced.
Well, you shouldn't be. Okay. You should actually take the time to go through and see what we're actually assuming. And there's papers published on this as well. Okay. So, all right, no further delay. How are we going to solve this problem? What ideas have you got? In your own, you're empowered to call on people here.
Okay. So the idea is pretty much to take the 3.3 degrees Celsius down. We want to get to what, 1.8?
Well below 2 degrees, striving for
2 degrees. Uri, but speak up.
Yaron, is it possible also to ask questions before we start playing with the model?
Sure, but I want to make sure that we actually build a scenario that creates a safer world for everyone in Israel and everywhere around the world. So what's the question?
Yeah, first of all, don't worry, we're going to have peace here in a week, so everything's going to be beautiful.
From your lips, lips.
Definitely. But I have a sort of like an overarching question. How does your model relate to or interact with the various IPCC scenarios? Because you sort of give one value at the moment.
Yeah. So one of the things that we've done, I showed you how we compare to the historical behavior for many variables. We've also compared and calibrated our model against a very large set of other models, IAMs, the models used by the IEA and other organizations. And, if you look at the scenarios of those other models, they don't agree with one another. Our model, we've worked to make sure it kind of goes through the middle of the ensemble of those other models. And the difference, I'm not going to show you this today, but it is available in the documentation. The difference between our baseline and a comparable set of assumptions in IAMs and IEA models and NGFS scenarios and so forth, the difference between ours and those is essentially statistically similar to the difference between any one of those other models and the others. So yes, it's a great question, and we've worked hard to make sure we're consistent there. And whenever we find a discrepancy, we try to trace down what are we assuming, what are those other models assuming that accounts for that discrepancy.
Okay, great. So let's start the interaction. What would you? Yeah, but leave time for the interaction.
Yeah, no more questions. I mean, it's fully documented. I'm happy to take the questions, but it's important that you put a little skin in the game here. Tell me what you think a high leverage set of actions would be.
Let's start with interaction, and we'll leave time for other questions, okay? So please, suggestion, what factor, what specific thing you suggest to change in order to decrease temperature?
Say nuclear energy?
Nuclear energy.
Okay.
We want nuclear energy in the Middle East.
Well, I'm not sure Israel wants nuclear power plants, more nuclear power plants, since they make very inviting targets, but that's
if you can speak up a little bit. Can you speak?
Sorry. So I'm not sure Israel really wants to build more nuclear power plants since they make very inviting targets, but nevertheless, let's implement a very large global subsidy for nuclear power. And what I'm going to do is I'm going to impose a subsidy amounting to 7 cents per kilowatt hour, which is huge. That's a gigantic subsidy starting now. And so watch here. We started at 3.3, actually, yeah, 3.3 degrees C above pre-industrial. When I add the nuclear subsidy, we get 1/10 of a degree of improvement. Now, every 10th of a degree matters, but that's a very low impact. So the first question is, well, did the subsidy lead to more nuclear? Well, nuclear is here. Let's look in more detail here. Yes, the baseline nuclear limps along because it's very expensive. And with the subsidy, there's a huge increase in nuclear power around the world. Why doesn't it make more difference to reducing the temperature? So yeah, so as a professor in the School of Management, I'm now going to call on somebody. Yaron, call on somebody, maybe the person who asked this question or suggested nuclear. Why doesn't it make more difference to the climate?
Why doesn't
Because make the renewables out.
Because what?
Make the renewable out. No.
Yeah, I think I heard that it's squeezing out the renewables.
The renewable out.
Yeah, so take a look at the energy mix here. And I'm going to take this subsidy away. So here's our baseline, lots of coal, oil and gas, and growing renewables. And when we add that, coal goes down, all the fossils go down, but it also reduces the renewables. So to some extent, the nuclear is cannibalizing the other zero carbon energy sources. I mean, look, the economic logic of this is very clear. You provide a huge subsidy to electric utilities and countries around the world for nuclear, and they're going to say, great, now nuclear is cost effective, let's build it. And as a result, they will also not build as many utility scale solar plants and offshore wind farms. So the self-cannibalization here is a huge contributor to the low impact. And the other one, of course, is it takes a very long time to build conventional nuclear power plants. Average of a decade or so. It varies around the world. I was an expert witness in the major legal dispute over the new OL3 plant in Finland. Just as an example, the contract was signed in 2003. It's a more than gigawatt scale plant. The contract called for first production commissioning and first generation into the Finnish grid in 2009. That plant only went online in 2023.
Speak up a little bit, John. Thank you.
Yeah. That plant only went online in 2023. An enormous delay and a cost overrun on the order of 10 billion euros. So the time delay and the cannibalization are the main reasons nuclear only led to 1/10 of a degree of improvement. And it's very, very expensive to subsidize because, as you can see here, this is the marginal cost of producing electricity. Renewables are cheaper than anything else today and projected to continue to fall because of R&D and learning and scale economies. Nuclear is here very, very high and stays high, which is why the market doesn't want it today. If you subsidize it, it gets cheaper, you get more, but that's a very expensive policy. So I'm going to leave that in the mix unless you tell me to take it out. What else do you want to try? Long way to go to get below 2 degrees.
What is next?
Lower population.
Lower population.
Okay, so lowering population compared to what it would otherwise be. We're going to reduce population growth. Now, how would we do that in the real world? We do it by well-known, proven interventions, better education, healthcare, and empowerment, especially for women and girls around the world, especially in the developing economies, access to healthcare, decent employment. Those are the policies that are known to reduce fertility and delay the onset of childbearing. And so, now, how much do you think that could reduce global population below the UN's 10.2 billion here?
What do you think? Is it gonna be okay?
I couldn't hear
very much.
Not much.
To 3 point what? 3.0?
Well, let's drop it by a full billion by 2100. So the end of the scale here, that is the 5th percentile of the probability distribution in the UN's projections. I personally think this would be an extraordinarily difficult target to reach, but let's see what it does, right? So I've lowered economic growth by so that our population growth, so we have a full reduction of 1 billion people by 2100. So what did it do to the climate? So let me put this back here. We're at 3.2 with our nuclear policy. Now we go down to 9.2, another 1/10 of a degree. Very low impact. Now, why? Why is it such low impact? Take a look here. Let's go back. Almost all the population growth is projected to be in the developing countries of the world. But that's where carbon footprints are the smallest today. And in addition, it simply takes a very long time for these changes to begin to manifest due to the long delays in the age structure of the population. So again, long delays and low carbon footprints for the people who would, whose population growth is fastest today and potentially would be much lower going forward. So,
okay.
what else?
What else? Yes. Electricity and electrification. Electricity and electrification.
Okay.
And renewable, but let's go one step at a time, okay?
Yeah, so we want to be good scientists here and try things one at a time. And of course, it's not linear, so there's interactions, synergies, and compensatory feedbacks, but let's do them one at a time. So let's try electrifying transport first. In the base case, we do have gradual electrification of transport, land-based. It is possible in the advanced settings to allow electrification through sustainable aviation fuel generated by green hydrogen from electrolyzing green electrons, electrolyzing water with green electrons. And so you could allow electrification of aviation and waterborne transit, but not for right now. So let's accelerate electrification of land-based transit. Now remember, where are we? We're at 3.12. Let's put a pretty large subsidy on electrification, and you get much faster electrification. This is the market share of electric vehicles, not just light-duty vehicles, cars and light-duty trucks, but long-distance trucking, buses, trains, etc. Much faster. What difference did it make to the climate? Less than 1/10 of a degree. Now, why is that?
Because it's still most of the demand is from fossil fuels. So
I couldn't hear. You're going to have to.
Because most of the demand is still for the fossil fuel.
Right. Where are you going to get the electricity to charge all those batteries? Take a look at the energy mix. Let me take this subsidy away. And now watch the energy mix here. Coal actually goes up. Gas actually goes up a little bit. Renewables go up too. But unless and until you simultaneously decarbonize the electric generation system, electrification, it's a good thing. It reduces tailpipe emissions, but it increases coal plant emissions. Now, I want to be clear. Everywhere in the world, electric vehicles are better for the environment and the climate than fossil-powered vehicles. But in countries like Europe and the United States, where we have much less coal, more gas, and a lot more renewables, the impact is much, much greater than in China, India, Indonesia, South Africa, that are very heavily coal dependent. The other thing that's going on, again, relates to the time delay story. So this is market share, but transportation infrastructure vehicles last a long time. So this is the share of the installed base. And you can see it lags significantly behind because vehicles just last a really long time. And that, so, you know, what we've seen in all of these cases, nuclear and population and electrification, is what we call the time value of carbon. You all know that you would strictly prefer $1 million today than $1 million in 2030 or 2050, obviously. In exactly the same way, as I'm sure many of you know, we strictly prefer a reduction in emissions today than the same reduction in 20, 30, 50, whatever, because every day that that carbon you emit now is in the atmosphere, it warms the climate. And even if you reduce those emissions later, you've got the damage that already occurred. So this is the time value of carbon. So we need to decarbonize the electric generation system to make electrification more effective. And you need to do things that have more immediate impact. So what do you like? What do you want to try?
Still at 3.1. Okay, the next one.
Try carbon removal.
What is it?
Carbon removal.
Carbon removal.
Great, we can do that. But you know, if you don't reduce greenhouse emissions, carbon removal is never going to scale enough to make a big difference. Now, I will do it, but before we do that, you've got a gigantic burden of greenhouse gas emissions, including the CO2 from the fossils here. You need to find some ways to reduce that.
Coal. Okay, coal, taking out the coal.
Okay, so how do you want to do that? How do you want to reduce the coal? I mean,
increase renewables. I'm just repeating what people say.
Okay, yeah, that's great. So one way would be to further incentivize renewables like we did for nuclear. So I'm going to do that. So where are we? We're at 3.06. Major subsidy for renewables. You can see the renewable wedge got a lot bigger. You'll also see, I think, that the nuclear got a little smaller. And now we're at 2.99. So that made a big difference. That's over 1/10. But it's not enough. So great. What else? How else could you reduce coal? And don't forget about the other fossil fuels, the oil and the gas here. How can you do that?
Reduce fossil fuels.
What fuels?
Reduce the use of fossil fuels.
Reduce the use of fossil fuels, but go
Sure.
with these things.
But how? How are you going to do that?
Don't say something in general. Look at the model and say, what do you want to change in the model? Okay, this is what we have in mind. Sorry? Afforestation.
Cut deforestation? Sure, we can do that. Now, in our base case, it's the black line. And you'll notice that even though we have not yet implemented a deforestation reduction policy. Deforestation is already lower than it is in the base case. Any thoughts as to why? Environmental science folks and ecologists, you should be able to figure this out. Warming is down by 0.3 of a degree.
So much deforestation you can do.
Yeah.
Forest will end.
There's I can't hear you, all of you.
How much deforestation you do?
The question.
In this ratio, you're not gonna have any more forest to deforestation.
Can you hear that?
No, I couldn't. I'm sorry.
Okay, so please share it with us.
Well, less warming means crop yields will not fall as much as previously expected in the base case, right? So higher crop yields, they're still going to fall, but not as much. And what that means is you don't need as much deforestation to produce the food that we need. But there's still massive deforestation, so let's reduce it. You know, maybe something like that is feasible. Well, now we're at 2.9. That's progress. Every 1/10 of a degree matters. But look at the mix of greenhouse emissions. You've still got massive CO2 emissions from the fossil fuels and methane. You've reduced the land contribution. But what do you think we need to do to reduce this gray band? That's the contribution to warming from coal, oil, and gas.
The carbon prices, the carbon price.
Carbon price. Okay, great. You haven't touched that yet. Our estimate is that right now the average global carbon price is essentially zero, $5 per ton of CO2. That's like nothing. And the reason for that is, although many countries do have carbon prices, many more don't, and those prices are very low. So any thoughts as to what magnitude of carbon price? Think global average. Some countries would be higher, some lower. Would you like to try out? This is hard. Most people who aren't in the climate and carbon policy world don't have a good feel for what reasonable carbon prices might be. So I can give you a hint. The US government considers the social cost of carbon, that is the net present value of the damage from emitting 1 ton of CO2 today. That cost is estimated right now to be about $190.
Wow.
And a lot of literature says it's higher.
So let's do it what, 50?
$50 a ton, okay? That would be, so
Yeah.
I don't know the price of petrol in Israel.
Okay, they say 100. They
100?
disagree.
Okay.
They want 100.
100. So I don't know the price of gasoline, petrol in Israel, but in the United States, that would be about 89 cents per gallon. So divide by 4, so it's, 22 cents per liter. So we're at 2.9. Let's try it. Boy, that's a big impact. We went all the way down half a degree just from the carbon price. Now, a little technical detail, I'm phasing it in over 10 years. You can, of course, change that. And then we're holding it constant. And it has a major, major impact because it disincentivizes all the fossils, and it especially disincentivizes the coal because coal is the most carbon intensive fuel. So coal is now very low. Oil is down, gas is down, renewables have risen much more to fill the gap. And because you still have an economy heavily dependent on fossil until about, well, at least mid-century, there's an incentive for everybody everywhere, industry, business, consumers, to be more efficient. So you'll notice that total energy demand goes down because everybody's becoming way more efficient. They're still getting what they need. This is a really important issue. Nobody's freezing in the dark here. What's happening is people are getting what they need. You need to remember, nobody wants a ton of coal or a barrel of oil or a cubic meter of gas. That's not what people want. What people want, need, and deserve is to be warm in the winter, cool in the summer, have access to good, decent jobs, healthcare, education, cultural opportunities, and connection with other folks. The best way to do that is efficiency. And so everybody's still getting what they actually need. They're just doing it in a way more efficient manner. That carbon policy is probably, it's the single most effective lever.
Yeah,
half a
I'd like
degree
to
of
comment
impact.
on that. So what you have here is a single policy tool in effect under energy supply, which probably impacts, well, we see that according to your model, impacts both the demand of, in coal, in oil, and natural gas, obviously. And the question is, why is that specific tool under that same scenario? Because what we could have done is just to bring down the levers for coal, oil, and gas, and ask ourselves how that should be done. And just the follow-up question, do you assume here in the model that income from carbon taxation will be producing subsidies? So will that be invested into subsidies for renewables, or just going into the general budget of the state and disappearing there?
Fantastic question. So the first one is, why not just regulate coal out of existence? So here I'm going back to the base case. Okay, this is the base case. And let's just regulate coal. And I can do that a couple of ways. So the first thing I'm going to do is I'm going to, starting now, I'm just going to ban new coal investment. Okay, just banning new coal. Existing coal plants would stay around. They gradually go away. That makes a difference, 0.3 degrees, right? But it doesn't affect directly the other fossil fuels. In fact, you're getting more gas now and more oil. You get a little bit more renewables too. But, if you phase out coal and you don't do anything else, like pricing carbon from the other fossil fuels, you're going to see more of those fossil fuels used, and that undermines the benefit of phasing out the coal. So I think that's the answer to the first part of the question. The second part of your question is far more important, and that is, what would the economic impact and the equity impact of a carbon price be? And here, this is a difficult question. The equity impact, if all we do is put a price on carbon and take all the revenue and put it towards the general budget of the different countries, it would clearly be a regressive policy that would hurt low-income people everywhere. It would hurt the poor and disadvantaged everywhere. And that's not going to happen, right? So how would you solve that problem? And there are solutions for this. Anybody have an idea? How would you keep the incentive effects of a price on carbon, but use the revenue in such a way that it protects the poor from the economic harm of higher energy prices?
Differential energy prices.
And I'm going to show you that's quite a lot of revenue. Let's see, here we go. So in your scenario, we have subsidies for nuclear and renewables, but look at that, the gray line, that's the revenue from the carbon price. And it reaches $2.4 trillion as the carbon price phases in, excuse me, and then it gradually declines because fossil carbon declines as a result of the policy. That's a lot of money. How could you use that money? By the way, this is the cost of your subsidies. Most of that is your nuclear subsidy. If I take that away, the subsidies go away. But what would you do with all that revenue to protect the poor? So I know you're not economists mostly. Would you like a hint?
Maybe differential taxing on poor relative to rich or something like that.
So yeah, if you say that low-income people don't pay as much as affluent people, then there's a problem. There's several problems with that. The first is, how do you enforce it? You know, you drive up to the gas pump. How are they supposed to tell who's rich and who's poor? So there's a huge enforcement problem here, and lots of opportunity for corruption and gaming the system. And it reduces the incentive that everybody would need to become more efficient and switch to more renewable and low carbon energy. So that's not likely to work. I'll give you a hint. Actually, it's not a hint. I'll tell you what I think is the way to do this. And that is, you take every dollar, every shekel, every euro, and you give it back to the people in those countries as a carbon dividend or a carbon rebate. And this, in fact, is already being done. Canada has a carbon rebate policy. So they implemented a carbon price a few years ago in Canada. It's about $50 per ton right now. It is scheduled to increase every year until it reaches about $170 a ton by, don't quote me, 2035 maybe. And every Canadian dollar of revenue from that is rebated to the citizens on an equal per capita basis. Every 3 months, everybody gets a check or a direct deposit. And if you're unbanked, you can go to a cash, like a Western Union check cashing place, and you can get your share that way. It amounts to, for a family of four, several $1,000s a year right now, even at $50 a ton. That's a lot of money for a low-income household. It doesn't matter to billionaires, of course, but it keeps the low-income folks from being harmed economically. So this is great. We're at 2.4 degrees.
So given that we live in buildings, and industry is very important in our modern life, what about energy efficiency and electrification in buildings and industry?
Great. Let's electrify buildings and industry pretty aggressively. We'll also do more for transport, and then energy efficiency in buildings, residential, commercial, and in industrial facilities. That helps a lot. Even though we already have $100 a ton carbon price, which is incentivizing all of those actions already, there's other market failures that prevent energy efficiency deployment. For example, in this country and many places, most people, especially low-income people, rent an apartment and don't own the building, but they pay the utility bills. So in that situation, the tenant would benefit from energy efficiency upgrades of the building, but the building owner would have to pay for those. This is a classic agency problem in economics and leads to a market failure, underinvestment in efficiency. This is a solvable problem. You simply have to write a contract that shares the gains between the building owner and the tenant, and this is actually happening in many places. So that problem is not solved by the carbon price, which is why even with the carbon price and your other actions, energy efficiency in the built environment still matters a lot, and in transportation also. Now we're at 2.2. This is terrific progress. What else would you like to do? Oh, and let me just say, the literature is very, very clear. Efficiency, especially in the built environment, is the fastest, safest, and cheapest way to get where we want to go. And I'll just give a little example. I'm coming to you today from my home outside Boston. It's about 100 years old and was originally heated by coal and then switched to oil in the 1940s for heating, and then natural gas. So 10 years ago, my wife and I did a deep energy retrofit here. The house was extremely inefficient, didn't have good insulation when we bought it, had the original single paned, horrible windows, lots of air leaks, etc. Deep energy retrofit, you're all probably familiar, so lots of extra insulation, really good windows that are very efficient. We reduce the air infiltration and exfiltration by 90%. We put in heat recovery ventilation, so there's fresh air in every room all the time, but without wasting the energy for heating and cooling. We completely eliminated the natural gas that was providing heat and hot water and replaced that with heat pumps, air source heat pumps, and heat pump hot water, and high efficiency appliances and LED lighting everywhere. And we put solar on our roof. Well, 10 years later, we have made 30% more energy than we use with no fossil fuels at all. And that surplus means I have no heating bill, and we're in a cold climate here. I have no electric bill, and the electric utility owes me $5,200. So what we did about a year and a half ago is we traded in our fossil-powered cars, and we have 2 electric vehicles now. I'm a bicycle commuter, so I don't drive that much, but whenever I drive now, it's 100% electric. And we can power those 2 cars for free with energy that is 100% carbon free, just out of our annual surplus. That's the kind of potential that's out there with energy efficiency. So 2.2, y'all have made tremendous progress, but we aren't where we need to be. What else do you want to try?
Where do we want to go, guys? And I still want to have a few minutes to ask another question. So
yeah,
any other idea? Huh? You know, you come with, I mean, agricultural emission, and the coal was down actually before. So yeah.
Yep. So I'm going to reduce agricultural emissions, and we know how to do this, and that helps. There's another 10th. I heard earlier, and I promised we'd go back to carbon dioxide removal. So nature-based solutions like afforestation and regenerative agriculture, we can do that. We're at 2. Technological carbon dioxide removal, very expensive, unclear that it can scale much, but I'll put a little bit in. Now we're at 1.9, and then waste and leakage is the other area you haven't really touched. And if we reduce that, here we are at 1.7. Now, when are we supposed to end, Yaron? Soon, right?
Yes, as I want to ask you another question. So,
yeah. Before
yes.
you ask that question, I just want to have everybody notice 1.7 is a much safer world. It's not safe because it's still worse than we are today, but it's a much safer world. So limiting the warming, air pollution is way down, saving lives, boosting labor productivity, and therefore boosting economic growth, helping kids do better in school. Crop yields are still going to fall, but not nearly as much. Deaths from excess heat at sea level, all will be better. And let's just take a quick look at what this might mean for you all. So let me make that larger. Okay, so here's the baseline, right? 3.7 C of warming, roughly where you are. Well, I guess you're closer to here. Okay, 3.7 of warming in the baseline. In your scenario with 1.7,
we saved Israel. Yeah. We
much safer, and safer for all of the countries around you, which greatly reduces the risks of climate refugees and conflict. So tremendous improvement. And what about the economy? The economy is going to grow more because of all the climate damage that wouldn't occur at 1.7. And you'll notice that you've done that without the need to assume any radical, magical, technological breakthroughs. Everything you've done here is doable, largely with the technologies we have today. And that's important because it means that the problem is not a science problem any longer, and it's not even an engineering problem, and it's not an economic problem because you can see the economic benefits. It is a social and political problem. So congratulations.
Yeah,
this is a much better scenario.
Thank you very much for helping us. And, you know, this is really exciting. It sounds really wonderful. My question, and actually it's not only my question, I was asked to ask the question by someone else too, is, you know, models are really, really nice and they can serve for all kinds of purposes. But what we want sometimes to know, and what is really important, is how impactful the model is. And do you have any evidence that En-ROADS really does the job, or it's just you know, a nice game?
Yeah, that's a great question. If it was just a clever simulation and people pull the levers, but nothing happened in the real world, we would all have wasted our time. So this is a question we've spent a lot of time on. We've published 3 peer-reviewed papers so far, 1 new one under review, assessing the impact. And these are all open access, I believe. Let me show you a little bit of the evidence. So this is not the scientific evidence, but just to show you what it does. Before an En-ROADS workshop, we asked people using Poll Everywhere. So they go on their phone, I am blank about climate change. And you can see what they say. I'm concerned, extremely concerned, frustrated, anxious, terrified, angry, overwhelmed, heartbroken. Then they experience a workshop using the tool, somewhat similar to what you've done. And here's what they say at the end. I am blank about climate change. Now they're saying I'm hopeful, energized, gonna do something, passionate, committed. This is really important because if people don't have hope, they just won't do anything, and then everybody's going to burn in hell together. So that's the anecdotal. Now here's the research. This is from the paper that's under review. So it's under review. It's not published, not peer-reviewed yet. So on these 6 dimensions of, do they know what causes climate change? Do they feel urgency? Do they feel any hope and empowerment? Do they know what the high leverage policies are? Do they plan to do something in the real world? And do they feel like what they do might matter? Agency. This is the pre-survey results for a sample of about 111 people. After the workshop, large and statistically significant gains in all of these, especially empowerment, intent to act, and agency. They learn more too, but it's the emotional dimension that drives action. And 6 months later, there's been a little drop off, but still large statistically significant gains. And some of these people not only expressed the intent to act, but actually went out and did something. So we do have some evidence that it really does matter. And what we need to do now is scale it up. So what you all can do is you can help by using it in your settings in education where it's very effective. We run role plays with it. This is from a session I did last year with our MBA students where they play the roles of the different parties in the global COPs and negotiate face-to-face. And then we run their suggestions through the model live. And the ratings are very, very high for this compared to other leadership and ethics workshops that they had. We just ran it a month ago, less than a month ago, for all the incoming freshmen at MIT. We had to do it in two sessions. And then I'll close with this, and I know we're just almost at time, but one of my colleagues ran an experiment at the local public high school. So what she did was this is the control group. She gave a typical talk about climate change that's in the standard curriculum that high school kids might experience. And you don't need to hear what she's saying. Just look at the picture. Is anybody learning anything in this room? And the answer is obviously no, because lecture is boring. So here's the treatment group. Same kinds of students. What they did was they were assigned the role. This young man is the president of the United States. These other folks are playing the leaders of other countries. They negotiate face-to-face, and their suggestions are implemented in the model right in front of them. See what happens. And let me just show you what's going on here. Now, I hope you can hear it, but what's happening is all these other leaders are beating up on the US president to fund loss and damage and pay for the transition in the developing countries. And he's pushing back. Where's it going to come from? Where's the money? Why is it in my interest? This is the difference. This really works. These kids are learning something that they aren't learning any other way. And I got to tell you, it's the same when I go to the Congress. So what I would encourage you all to do is take a look at the model, decide whether you think it's scientifically rigorous, tell us what you think needs to be improved, but go out there and use it in your research, in your teaching, in your engagement with policymakers. If you like, we would be glad to connect with leaders in your networks where we can run workshops like this, either online or in person, for all of these critical constituencies, the groups that we must engage with in order for policy to be enacted. You can become an ambassador with En-ROADS and learn how to do what we've done today and more with training materials we provide for free, and then bring it to your communities, bring it to your shul, your temple, bring it to your school. Everybody finds this people love it. I'll just say that. So with that, I know we're a minute over, Yaron, but thank you all very much. And I'll be happy to take any last questions if you have time. If not, I understand perfectly, and I'll get you all the slides.
Thank you very much, John. It's very inspiring. I would like to mention that we have some plans to have the En-ROADS Israeli chapter, and I hope we'll be able to start it soon. Thank you very, very much, and good luck, and keep up, the great stuff you do. The world is better because of what people like you do, and we will join you.
Thank you very much. But honestly, it isn't about me. It's about everybody here in that room. Everybody needs to stand up and take action to create that safer, healthier, more secure world we all.
Amen. Amen. Thank you very, very much.
All right. Thank you very much.